Alrighty then. That says we're live. Guys, what's going on? Memes here, yes. And we are back on Planck Week, yes. It's the Shark Week without necessarily sharks, but sharks are made up from the elementary building blocks of our realm. Therefore, sharks are Planck. Planck are sharks. I'm grasping for straws here, folks. All right, so long story short is we're going to be talking about the Planck Mass today. What the heck is the Planck Mass? According to the standard model of particle physics, it is the largest unit mass, or the most massive unit mass that we could have. Because, oh, Planck mass is like 10 to the minus 8 kilograms. You're like, all right, maybe a full iced coffee is like a kilogram or so. It's like, yeah, you gotta divide this into like 10 million little parts, and then you get a Planck mass, aka about the mass of a mote of dust. Extraordinarily small. However, by the magic of E equals MC squared, the energy you'll get out from the Planck mass is essentially the energy in an average strike of lightning. You're like, wait, hold on. Mote of dust to call lightning. It sounds like some wizardry to me. It's some metaphorical speaking, yet uh, any sufficiently advanced technology is indistinguishable from magic. If you can convert a grain of dust into a lightning bolt, by definition, that makes you a wizard. Uh, Apparently, CERN has a lot of wizards. But I digress. Okay, so let's go to our little thing that we've been doing before. We gotta go to the Planck Mass before myself and Viz go on an expedition to actually discussing the new moon of Uranus later. Because we had that episode like a month or so ago, and I realized I was talking a whole bunch of hot garbage. Talking about something from 150 years ago. Fast forward like 2 or 3 weeks. It's like, okay, now that title actually fits. But for now, we're going to be discussing the Planck mass. And again, the link to where I got this is in the doobly-doo below, where I got it from Wikipedia. Okay. Now, again, take that for what it's worth. Trust, yet verify. Uh, but even when you go to Wolfram Alpha, this is essentially the definition. Basically, you got the Planck mass. What is this? Small m for mass, big sub p, because it's a Planck. It's somebody's name. All right. What is this? It is the radical, aka the square root of H bar, the elementary unit of action. C, the speed of light in a vacuum, aka the medium. Divided by big G, the Newtonian gravitational constant. For those of us that have been paying attention, the primary Planck units, they're all using these three constants. The elementary unit of action, the maximum of speed, and big G, the Newtonian uh, gravitational constant of proportionality. That sounds right. I'm sure somebody can correct me if I misstated that. But yes, welcome, crypto. Yes, welcome. Yes, feel free to interact with this video however you want. I ain't your dad, as far as I know. So feel free to spread this around. Uh, Hit whatever buttons you feel work there. Okay. So we've shown the thing. Let's go back into our friends over here. We'll share the little window. And again, don't. Oh God, what am I showing? Uh, Not that one. Not that one. Here we go. Okay. So don't mind my background music. In Godzilla Final Wars, it soothes me. All right. So again, this is the modern value. You could, as long as you're expressing these in coherent ways, that's ultimately what we're looking to do. Because, for instance, yesterday we were going over the Planck charge. I've had to start doing some more thinking because it depends on how you want to express it. Now, if we look, I've been doing it this way with the 4 pi and the radical. Okay. Now, to be fair, if you want to simplify it and not have the 4 pi there, you can just have h bar, your elementary unit of action, the speed of light, and then you just need the electric constant. You need the electric constant to get out some form of charge. Okay. So this gives it out in another way. So it's about 3.3 electron charges This way, it gives it out like 11.7 RKA, the amplitude of the fine structure constant. So this is kind of how, or at least this is how I generally describe it, because when you take this magnitude of charge and then you put it in, uh, this basically the Planck charge and the Planck mass unify at the Planck force in respect to each other in regards to the Planck length. So I had made this argument before, and but then again, it's like, oh, what's the best way to express something? Because normally, if you have what was it? So you got your Planck charge, multiply it by another Planck charge, okay, and then you divide the whole thing by an equivalent radius. So what is it? 1/r². So that's typically how stuff works in physics. So all we're doing is our radius, just using the Planck length, so the minimum of length. So the interesting thing is, the claim is the maximum unit charge. This is the maximum unit charge. So we've got charge one times charge two over our radius squared, but we need just a little bit more. It's a little protective brackets over there. Just let me do this. So it should line it up a little bit better. But we need some form of constant of proportionality. Basically, we need Coulomb's constant. Constant. All right. So when we take our first charge, we're effectively squaring because we're multiplying it by the same thing. So we're squaring it, divide by the Planck length. It gives us bada boom, bada bing. Okay, the Planck force. So that's my justification for using it. Now we're doing mass today. We're not doing charge. So what do? We can do something very similar because as we can see the Planck mass right over here, it's mass. We got small m sub big P. We got our radical in there and everything. It comes out to be these approximate digits. We got our error over here. So basically, the Planck mass, to the best of our calculations right now, is approximately 2.17644 times 10 to the minus 8. And we have an error in the last two digits of 2.4. So that means this could go up to 5.8, or it could go down to like 2.0. And that would be one standard deviation from where we believe it to be. So typically, if you're within one standard deviation, you don't really need to have to explain much. If you start getting out there, you need to kind of explain why. If you're like 5, 6, 7 standard deviation, you're going to have a pretty good reason. Maybe physics as we know it is a little bit off. Now we know it's not complete, but before you're going to say everyone else is wrong, you need to have a really good reason. And you know what? There might be some very good reasons. I'm biased. I'm biased. I have my own reasons. I have reasons that would help my own self-interest. Duh. I mean, why wouldn't you be honest about that? Do you need to go around and be like, do the whole, I'm going to stand on my soapbox? It's like, I am obviously right and blah, blah, blah. Use charisma here. This is the only way it can be. Yeah, people do that all the time. Doesn't mean they're right. I think, yeah, at least for me, like, I think some of the best scientists I've run into, they'll just be like, yeah, I could be wrong. Could be possible. It just express that there's doubt. Now, maybe there are some arguments that you're like, okay, this has to be it. Now, I ain't no god or prophet. I'm gonna do it on the internet. I'm just basically saying how I see it and stuff. Uh, oh, thank you. No, thank you, my dude. Uh hey, don't get me wrong. I love nice words. Who doesn't like to be flattered and stuff? Is it important? I don't know. Ultimately, it's history is gonna dictate whatever it is. Uh, because sometimes maybe you find something and it's like, even if you find something and even if you share it with the world, it doesn't mean it's going to be picked up upon because, well, people are busy with their own lives and everyone has their own little thing. Uh, I just look at history and sometimes, like, some of the common names, like, well, here nowadays, it's like, whoa, this person must have been like total superstar back in the day. You found out it's like, well, somebody like Boltzmann and stuff, a lot of people like hated on him so much that ultimately I think dude man ended up taking his own life. You're like, huh, some of these people were bullied. They died penniless and alone. Some folks literally, their ideas were so out there, they literally didn't need, like, they handed it to somebody to be published on their deathbed. They were so afraid about like critique and everything. Now let's add in the dynamics of social media. What could possibly happen, for better or worse? But again, that's a little bit of a personal rant there. Oh, so I was commenting that bang on coherent wave geometry interaction, the key to it. I mean that sounds right. That sounds right. To be fair, Nerdy might agree with that. Nerdy's been playing with a lot of really interesting stuff, so still need to get Nerdy on at some point to go through it with me. Just because the one big thing about not being like super well known is that I don't have everybody sending me things. Surprisingly, I still have people sending me things on a fairly regular basis, and some of it's very interesting. I feel bad because sometimes it's like there's so much stuff here. It's like, how much time do I have to really go through this? That's why I like to sit down with people because I kind of do the Stephen Wolfram thing. If it's right in front of me and I can play with it right there, and I have the person that can actually guide me through it rather than like all I know is like the first time I went out to Utah to the Physics Monastery, actually having Dad sit down with me, it's like, oh my God, this makes things so much easier. Having somebody there to actually like explain it rather than it's like, all right, I'm gonna do this on my own because I'm sure I'm a clever person. I should be able to figure this out. I find out I was not as clever as I expected. But mostly that's the thing. That's the way I look at it. I'm like, hey man, all of a sudden, giant 7 foot tall flaming gummy bear crashes through the roof, and that's the end of me right there. Hey, at least I said a bunch of things. Maybe in 1,000 years, if we haven't obliterated ourselves, some internet archaeologist will come around and be like, "Oh, that seemed to be a good idea." What were people busy doing at that time? I don't know, arguing about Kardashians or whatever the hot topic of said day was. Hey, whatever. To each their own. It's Yes, nerdy. You are correct. The louder one shouts, obviously that makes you more correct. That's what I've learned from cable news. So yeah, I saw it on TV, so it must be true. And insert whatever platform you want to say there. So okay, so back to the Planck Mass. So I got this stuff here. So basically, as we can see, we've got, and again, the interesting thing is these are all radicals. Some may make the argument that, well, and at least I've heard this on some of the physics stack exchange boards is like when you're doing some of the Planck length, it's like, well, if you take the radical off rather than getting a length, you're going to get an area. Would that mean that the squared value or area is more fundamental because we don't need to take the root? I don't know. Are there other roots more fundamental? At that point, like that might raise the question: is the square root of -1 more fundamental than one? The ideas that go through my mind occasionally. It's like, I don't know, what if rather than thinking of one, next successor, we should be thinking of -1 and just going in a different direction on the number line, really. It's the same proportionality, it just happens to be a negative. You take the square root of that, something complex numbers, hey, you get your real component, you get your complex part of it and everything. I don't know. At that point, if you get like that seems to have some notion of fourness to it because it's like, all right, 9 degree rotation, 90 degree rotation, 9 degree rotation, 90 degree rotation. All right, we've literally come full circle. Um, I'm not a mathematician or geometer, but these are the things that I think of. Uh, let's see, where are we at? The, Ripto, that's a That's a very bold, strong claim. I have no idea about that. I've heard some very interesting science stuff that's going on about being able to extend livelihoods as far as the elixir of life about gold and silver water. I mean, that the closest thing I know to that is Goldschlager. I, at least that I know of, my only problem is I'm like, If I take some shots of Goldschlager, if I ever need an MRI, I think I'm screwed. Because won't all those gold lights just start ripping through me or something? I don't know. I mean, that would be awesome if that was the case. I just haven't heard anything about that, so I can't say. Uh, everything's oh God, some scientist. No, no, no. See, it's sometimes people like to. Okay, there's something I've learned within the realm of politics is what you can do often is you can go, you throw on your suit jacket, you throw on like a nice, you make yourself all spick and stick. You make sure you have the nice crew cut or $600 haircut, whatever it is. You throw on all your makeups and all your birthmarks and everything. Go. You make sure you're clean shaven. Then you go up there and you speak very clearly and eloquently with confidence, and you might be throwing out a whole lot of hot garbage. I did sales for a while. I've, it, uh, again, I don't have a problem with somebody making an honest living. It's just, just follow the incentives. What's the incentive? It's like, well, I'm a dude, I have an idea. Okay, now you might have an idea, and it's one of those things where if you're ever going to call to somebody, it's like, we saw you'll be great for our business. Oh, what's your business do? Well, we'll talk after you join. So what you're saying is you're trying to get me to sign up for something, give you my information and probably some money before you will actually tell me what the heck that you're a phenomenal business. That's absolutely amazing. If if you can't tell me what it does, it sounds like you're deceiving me because you're saying that something is so great and so wonderful, but you can't tell me what it is. That's the thing. For sales, it's like you can make up for having not necessarily a really great thing. Heck, it's the whole adage where if you have a good enough salesperson, they say, "Oh, they could sell a catch a popsicle to a woman wearing white gloves." For those of no, ketchup tends to be quite sticky and very deep red and can leave very brownish marks, aka a woman wearing white gloves probably wouldn't want a ketchup popsicle. That seems antithetical to the wearing of pretty white gloves. Uh, that's all it is. And again, it works aggregate on scale, just a statistical thing where it's like you say a whole bunch of things with confidence, and then somebody's like, oh, well, that kind of resonates with me. So I'm just going to go around and say it. And that's how those memes kind of progress. And it's just hilarious. Sometimes you go on Twitter, it's like you see all these things. It's like you see the note, you're like, all right, so this was just complete BS there. And the best thing is the thing that I learned from Naked Gun is okay, at one point, again, spoilers, I know like 30 something years later. And the Naked Gun, they said, quote unquote, something along the lines of the best assassin is the one that does not know that they are an assassin. Because basically, it's some mind control thing that would just set a program in their head and they would do it. Because well, if you don't know you're going to be it or do something terrible, then how would you know? Ultimately, I think there are a lot of folks out there. A lot of folks will say, oh, these folks are grifters and everything. Sometimes it's like they just saw something. And again, some very minimal research will show that like this is incorrect. Like I see some random large account that talks about space on Twitter and blue sky, and it's like, yes, yes, it's like this this star or whatever is like 8 million, or it's like something like 80 million miles away or something like that. It's like oh, Betelgeuse was 80 80 million miles away. We'd basically be screwed because it would literally have fried us already. Um, it's it, they are off by like light years and stuff like that. They're using the wrong thing. So it's like, all right, before you post stuff, you could literally just go to either Wikipedia, like Wolfram Alpha. It's like, how far away is this? Okay, X number of light years, or 10 to the 8 million mile, or whatever it is. It's like, that was a very simple thing that literally you could just do a basic Google search for if you want to see. It's like, this is you just pretty picture some words, and a lot of people are like, oh, this is fantastic. This is great. I'm sorry, I'm ranting on people here, but where are we at? Oh wow, we're talking all types of stuff here. Uh, oh, dude, well, that see, that's the thing. Crypto. My general thought is any sufficiently crazy idea is indistinguishable from madness. It's something may seem like such a crazy idea. It's like, well, that person's obviously mad. It might literally be a stroke of genius. Perhaps this is the way things should actually go through. It's like, but again, it's like I'm not a doctor or anything. I can't tell people to be like, yeah, I can't recommend people going on drinking metal and stuff like that. Just inherently to me, that seems like a bad thing. Uh, then again, I'm not a doctor, so please consult your own personal physician. Okay, so apparently Goldschlager is probably not a good thing to chug down. Yeah, it's. I was wondering, like, how the heck are you selling this stuff? You have people drinking metal? That just sounds like a bad idea. Let's see. Da. The answer is 42 potentially. I don't know. It's Planck momentum squared is about 42. So, what is it? Planck momentum squared. Yeah, it's like 42.57. So it's the only reason I know that sometimes it's like when I play around on occasion, I'll do some other things. I'm like, what the heck is this number? And I'm like, ah, just take the square root of it because if you get all even exponents here, it's you just take the square. It's just gonna half all that stuff. So uh, that's the thing. As long as the multiple of two, you can take the square root. Or if it's large enough, you can take the cube root and everything like there. All right. But let's go back here. Let's talk about. We're talking about the Planck mass. So let's actually get to it. So we had Coulomb's constant over here. So okay. So the reason why I considered that magnitude of the Planck charge is because when you set it to Coulomb's constant, it ends up being the Planck force. Now, you could have the argument that maybe epsilon naught, the electric constant there, if you set it equal to that, if it comes out to be the Planck force too, then hey, whatever. But this is just relating Coulomb's constant there. So if we change this from Planck charge to Planck mass, so we go there, Planck mass, so we got a mass one times mass two, and we're dividing it by that Planckian r, aka a unit of length. That's all it is. We square it, but instead of Coulomb's constant, we need another constant of proportionality. We need big G, Newtonian gravitational constant. Okay, and just set it as a unit, just so we know, and then we get basically the same numbers. You get the Planck force. So basically, at the realm of the Planckian limits, so to speak, when you have the Planck mass, you have two Planck masses, and then you take the distance between them as a Planck length and you square it. Newtonian constant of proportionality, the gravitational constant, gives us the Planck force. So that's why I like using these different those factors, or at least also that's how that basically explained it to me. So I'm like, all right, if you have these different factors, and then you can reproduce the other stuff that we see in our world, or at least according to quantum field theory, it's like, all right, maybe there is something here. Again, could all just be wrong. That's it. But I'm like, if I'm able to start doing calculations and they start leading to interesting things, and we might be able to explain a bit more with it, well, isn't that what we're trying to do? We're trying to find pockets of computational reducibility within our world. Because if we do it well, rather than having to, ju- rather than being here and being able to talk with you all, literally, folks being able to remote view from thousands of miles away near instantaneously, I would have to write a full letter, address it, send it out there. Have it physically delivered. Have somebody open it up. Be able to go through all this. Bada boom, bada bang. It's like, all right, no, we just send a little oscillation of some waves going through some lines up into space down here, being beamed in through satellites or up through some switching station and everything. It's literally freaking magic to me. So Uh, let's see. Oh, damn. I literally, no, you look like you're in your 20s, man. Good for you. Let's see. Let's see. Hey, welcome to, oh, you are from, where in Portugal? The conference I went to, I don't know if we talked about this. It was in December. I just remember flying into Lisbon, and then eventually, after talking with some taxi driver type folks who apparently in Portugal, that your taxi driver isn't necessarily your taxi driver, but they're mostly your drug dealer apparently because of the laws. The long story short is we were looking for a ride, and the taxi driver told us to take an Uber because he was busy with other things. So, uh, it is what it is. But let's see. That's a until the crowd understands. Ah, 618. Uh, well, my mind filled in 6187 times 10 to the 34 meters. I'm sorry. I'm sorry. I'm just a lame language model nerdy. It's the reason why I say that is because what is it? Meters squared divided by the Planck length gives you the inverse of the Planck length, but in the same dimension of meters rather than inverse meters. And it comes to 6.187 times 10 to the 34 meters. Again, it's a little toy mod. Basically, the claim is with taking length square as a constant of proportionality. Huh. That's, I'm literally just realizing now from just going over this little exercise that, okay, so number one, I really have no way to justify this. The claim is if you take, okay, this is getting interesting. Is what I end up doing is, okay, this is a little short. This was inspired by Dr. Salvatore Pius and Rick DeWitt because there's something you can do where it's what is it mass of universe by volume of universe. No. Mass of universe divided by volume of your universe. I think we need age, age of universe. Uh, there, and we need something else. That should be age of universe. Okay. I think that's it. I think we go. What am I trying to do? I'm trying to get an equivalent of force here. So mass, age. It's just like big G. How do I say this? Just put that up there. Move this down here. Might need to square the age of the universe. Okay. But basically it was a way to hold on. I need to find this now. Let's give me just a moment. Uh find this. I know I had this somewhere. Yeah. Where are we going? We're going to okay, we've got Piper the little Mermaid down there with the crazy eyes. I'll make them all beg me for their lives. A terrible person. Oh, my friends don't deserve me. Oh, excuse me, I don't deserve my friends. Strike that. I need the inverse. Ah, Planck force. Here we go. Uh, did I actually? All right. All right. Oh, I need to convert it into energy. Duh. All right. So total observable universe mass, speed of light squared. Okay. Times the radius of divided by the radius of the observable universe. All right. So it gives us this many newtons, which it's of magnitude, the Planck force. So how much different is it? I think it's like 8 pi-ish. Like 8 pi, I think. That's 1/4 of the Planck force. So it's 4 pi. It's two. We have about 2 pi. Well, how about this? Rather than doing that, let's divide by the Planck force. They'll give us at least like four significant digits. All right. What does that look like? Looking for a closed form. What do we got? Uh, generalized magnitude estimate. It's about six off, so whatever, 2 pi-ish. So basically, if the Planck force does seem to be a thing, so uh, okay, so let's go back. Oh, oh God, I was doing that wrong. Okay, radius of universe, and then mass of universe, and then we just multiply by c squared. But boom, this should give us okay, about a quarter of the Planck force. Close, it's close, but that's an interesting thing. What if we took that seriously? Okay, so if you took something like that seriously, you can. The heck did I even just do? Okay, I just did the same thing just with charge and stuff, and it's yeah. Um, the long story short is, if you have something like that, you could do like Planck force, and basically you just set it proportionate to what did we do? Uh, back. Yeah. So what one could do is literally x kilograms. Just solve for x, because we're saying this equal to the Planck force. So as long as it's dimensionally set up correctly, I think we have the dimensions set up. Okay. So this is estimating. We're solving for estimated amount of mass in observable universe. What is this? Okay. So this giant number times 10 to the 53. We only had like four significant digits, so we're solving for kilograms. So let's see, kilograms. So as we had calculated before, it's roughly about a factor of four the mass of universe in ordinary matter. What if we assumed it was true? So if we assume this was true, I know, I'm going all the way around to get back to a point, but we're talking about the Planck mass here. So let's get back to our point. So, all right, so we got all that crazy stuff there. So what happens if we did something like this? Let's say our constant of proportionality there. We had, I'll just do meters. And we're going to do meters divided by the Planck length and square that whole thing. Now, again, we have a dimension of length there, or and then another dimension of length. Since the dimensions of length cancel out here, we're basically just getting the raw number, a dimensionless number, if you would, the ratio between the meter and the Planck length squared. So it's giving us this number here, this 3.828 times 10 to the 69. All right. Now, what first drew me to that number was I actually listed it as like a hypersphere operator because literally take a dimension 4 hypersphere and then I had, I don't know, like 30 something, 30 or 40 digits there from Thad's calculation of the Planck length. Just I'm like, all right, could be right, could be wrong. It's just going to give me a bunch of digits. So basically, it gives you the radius, which is 1 over that. So basically, this is what I input. And, oh, why is that? Did they change something? Okay. But long story short is the equation here with all the different variables to calculate the hypersphere stuff gives me this 3.828 times 10 to the 69 number. Just inverse Planck length squared, just without dimensions there. Okay. So I just view that as like a hypersphere operator. And I start playing around with different numbers. And again, this is a toy model. In order to justify this is the thing, one, you're going to need to show some significance and that the meter actually has like true significance aside from it being coherently put together that way. Now, might that be the case? Maybe it is. The the Because ultimately it's the relationship between these different dimensions of measure. All right. So we got some measurements, we've categorized, and we've managed to put these different forces, so to speak, in different phenomena into different groups that seem to meld together. So, like length and time. The meter may be arbitrary, even maybe in the second is arbitrary, but the relationship between a distance, a length, so to speak, and the time, or perhaps maybe an interval, might be a better way to say it, is the constant of proportionality, c, or at least that is the maximum. And you might have different variables there, but if you have a minimum of length traversed in a minimum of time, you're going to have the maximum of speed, right? A minimum divided by a minimum. You got something really small divided by something really small. It's going to give you something really big, right? It's just how things work, right? But okay, so we have this number here. So the interesting thing is, you take that. What if there was some there? All right, there was some there. It's like, all right, well, what if I assume there was some relationship? And I'm getting to this just because of our last little exercise. So why do things seem to drop off as r squared? This is pure speculation. Now let's you get the warning. It's Professor Wolfram. All right, here we go. Buckle up, folks, as we conjecture
Although
ahead.
this is going to be weird, and it's going to be about a different.
Title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one Roolead. I don't think it rules them all. And it might be just hyper Ruleal turtles all the way down.
Yes, it's on the back of an infinite number of hyperruleal turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
I was copy. Thank you. Uh, deep floor. You had to be at the conference. But I digress. All right. So the whole claim is, all right, I got a reference of length, dividing it by a Planck thing. All right. A reference thing and a Planck thing. Could we do something interesting? Now that's a really big number, so hypothetically, what if we thought there was some there? And we just solve for x kilograms over, I don't know, we're looking for a big thing. Let's divide it by the maximum individual thing. Planck mass. All right. Boom. So basically what we're doing is we're taking the ratio of the meter in regards to the Planck length. We're taking that squared relationship. So we literally have the one of reference divided by the one of length squared relationship. And we're going to solve for x kilograms. In order to find that amount, we're going to divide by the Planck one of mass. Cool. What do we get? Some ginormous number. Okay. So we're getting 8.3315 times 10 to the 61. Okay. Now we're solving for kilograms. Let's remember that. We'll cut it off here. We only had so much information we were putting in, so we get that many kilograms. What the heck is that? It's like 100 million times the ordinary matter in the observable universe. So long story short is with this particular toy model, called a toy model, it's like, I don't know, this is not going to try to confuse the map with the territory, because I look at this, I can line this up and be like, oh my God, this is so great. It makes so much sense. I don't know if there's any there. Now, there's interesting things because this number does kind of pop up. You don't really see it much, actually. Let's see if we see it. Boom. Oh, look. Oh, we look for 8.3315 times 10 to the 61 kilograms. What comes up? Oh, look. My social media accounts. The means of destruction, the means of destruction, something new. Okay, that's joules per mole. It's interesting. That looks for, it's from somewhere, Japan, maybe a power company. It looks like megawatts there. Uh, this looks like an Italian thing for, it's some, yeah. Okay, we got Cyrillic over there. I don't know what any of that stuff is. Yeah, okay, so of the one, two, three, four, five, six things that Google search returns, two of them are just me randomly adding in equations onto Twitter, X, or whatever the media platform formerly known as Twitter, which is still Twitter to me. Um, you don't really see it. Okay, so what happens? Okay, the strongest argument I have, and again, this is just a consequence for our input here because we need to be open about what the heck we're doing. So hold on, let me go snag that number. We'll go back to how we calculate it. Okay. So note, we are literally referencing meters squared here. Okay, I'm gonna show you this for a reason. Because if we just throw this here and we do c squared, so we're gonna take that amount of mass, we're gonna convert it over to its energy equivalent. 7.488 times 10 to the 78 joules. Okay. That's a crap ton of energy. But what does it mean? What could we think about it? Okay. So if we look at this number, and then we jump over here, we looked up something called the Planck spring constant, which it's not under Planck spring constant, but if we do the Planckian dimensions, excuse me, spring constant, and we look for its actual physical quantity, what are the dimensions that we have within our dimensions of measure? How is it expressed? The mass, and then there's times to the negative 2, which just means time squared, and the denominator. That's all. Time squared below. Okay. Elasticity constant, force constant, bond force. Okay, bunch of different things. Mass divided by time squared. So all we do is mass divided by time Square the whole thing, so this would give us the Planckian equivalent of the spring constant. Wait a second. 7.488 times 10 to the 78. No, 7.488 times 10 to the 78. Note, the dimensions are different. We got kilograms, meters squared divided by seconds squared. But kilograms just divide by seconds squared. Did you pick up on the difference? The difference between these things is literally just meters squared. Because I take this whole dang thing, we need to divide it into our little thing right here. Boom, 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 boom. So to speak, of matter within our realm. You do some calculations, but you're still see the proportionality factor. Which, disclosure, I mean, if I am literally entering that in the calculation. So at that point, again, even if there was some there, now you're going to have to justify saying that the meter has some actual significance. Is it just a consequence from our particular system? I don't know. I mean, it's interesting because the kilogram actually was originally defined as like 1 cubic deciliter of water, which water itself is interestingly enough was hold on, let's just do uh, 1 gram. Remember, 1 gram is the 1 gram is approximately 1 cubic centimeter of water. And again, that's assuming that you have coincidentally 1 meter of water of cubic water is 1,000 kilograms approximately. Now, to be fair, the maximum water density or water density itself, it matches for about 3 decimal places. If you have a particular pressure and maybe like a little bit of salt in the water, you can get to precisely 1,000 kilograms. So, but at that point, you're going to need to have to say what's the justification for basing like a fundamental unit on water? I mean, that would be crazy. I mean, water is something that comes about after we get going. I mean, that would have all type of potential inferences there. And I don't know. See, the best I got right now is the Planck momentum, which we had taken a look at before, is of magnitude 1 in reference to these things. So that's the strongest argument I have, unless there's something that's not publicly known that people have been working on, but that's another story. Hey, welcome, Tommy. Oh, hold on. Trouble with sound. Let me see. Uh, uh, let me check my thingy. Let's see. Where are we at? What am I looking at? Hold on. It's camera. Blah blah blah. Give me a moment. Audio. All right. Audio seems to be transferring. All right. All right. Okay. It's at least showing it's bro. Oh, I should probably actually check the dang thing. What a noob. Where are we? All right. One a moment. All right. Are we here? Bueller. All right. Bueller, we are here. All right. Cool. So I'll go back to the thing. So where are we at? We're supposed to be talking about the Planck mass. Okay. So let's actually do a little bit back to our Planck units here. All right. Let's get these to the point where it looks a little bit better. I'm begging these things. All right. Okay. So the factor of the square root of 2 pi. Okay. Because doing a cycle, we did, what was it? Planck's constant versus Planck's reduced constant, aka the difference is 2 pi or a cycle there. Because, well, maybe it's originally joules divided by frequency, and frequency tends to have, well, if you're going to have a cycle, there's going to be some form of a circular rotation, or maybe a sine wave oscillation, which when you line it up, you spread it all out, bada boom, it's going to be a circle. Something's waving, allegedly, in a vacuum or a thing. Yes, we continue there, and then we have our difference in Stony units, which is basically just 1 over the fine structure constant here. This is how Professor Feynman liked to think about things. Again, we went over yesterday. It's like there's the most profound and something, something, yada, yada, with the observed complete constant of a real electron. It's basically 0.0854, yada, yada. Basically, when you do 1 over the amplitude of the fine structure constant, you get this. So the amplitude is basically just its square root, because if you take the amplitude of something, you square it, and then you get the probability, stuff like that. And I believe that's what they use in quantum mechanics to figure out the likelihood of different stuff and things going on here. So this is just its 1 over alpha would be about like 137-ish. Apparently 11.7 is not quite as, so to speak, sexy as 137. I can understand why. Oh, 137. That sounds cool. That's like a prime thing. And to be fair, it's not 137. There it goes there. It's like when you have folks, you'll see folks that are like, oh, we figured out the fine structure constant. Why? It's like I did something and it comes to be like 137, and then you'll see like 5, and then like 04 and stuff. It's like if you're gonna make a claim, and especially like if you happen to be a particular researcher or something like that, and you're actually trying to make things there, you want to try to explain more with less. Now, if you're going to propose something and introduce something, that's fine. That's totally fine. I mean, people do that all the time. Does that have more explanatory power? I.e., if you're going to say this is what's explaining alpha, you're probably going to want more than 3 or 4 significant digits, because if we've got it to at least 9, and when we start to argue around the 10th or so digit, if you don't have inversely expressed 1 over like 137.035999, at that point you already have Euler's constant stuff. So does that have meaning to it? I don't know. It seems to match about 5 significant digits or so. You got to at least be able to replicate things or have a good reason why there is a deviation. Perhaps everything else is wrong. Now, if you just say that and you're just like, no, everyone else is wrong, that might be the case. Are you able to communicate that in a non-snarky way where you actually are attributing it to actual stuff that might be going on rather than your personal opinion and raging against everyone else out there? I can't say. Maybe it's right, maybe it's wrong. I tend to think usually the cooler heads tend to prevail, and for all those that want to sling bud, hey, my opinion, just legalize dueling. I say we let consenting adults engage in mortal combat under the doctrine of bodily autonomy. Let them fight so they can, quote unquote, destroy each other, because that seemed to be a big thing. And again, it's probably just my narcissism shining through. It's like, as soon as I started saying, we should just let consenting adults fight so they can destroy each other, I said that a bunch, and I don't see the term destroy all the time. I also don't see the term SJW around as much anymore. Again, I'm just the natural evolutional language and not an occasional troll just pointing out the obvious. Uh, let's see, where are we? All right. Oh, okay. And then within the Planckian system, this is interesting because you could show these different factors here. So let's just take a quick look. So area is length squared. So if we're taking the square root of this thing, we're just literally just ripping that radical off. So we're exposed here. We're exposed. All right. So this, okay, I mean, this is interesting. Can you even justify this? It's like the volume. It's like, well, you just take the length and you just square it there. Oh, no, I guess you could do that. Oh, look, a 3/2 for volume. That's interesting. Momentum. Oh, elementary. So Planck mass times the speed of light, which would be equivalent to the elementary unit of action divided by length, uh, because h bar is mass, area, rate. The mass, two length thingies, and you're dividing it by that. Okay. Or you express them this way. And again, you notice most of these things ridiculously small. 10 to the negative 70, 10 to the minus 105, 10 to the 9, 10 to the 44, 10 to the 96, 10 to the 51. No tens. Literally just at the first power. This is interesting to me because well, Planck mass is like 10 to the minus 8. The speed of light is 10 to the 8. So yeah, it's within our given system. We exist in the realm of the Planck momentum. I mean, ultimately, that's the best justification right now that I can really say about why might some of the stuff work. But then again, that would just be the order magnitude, because I think a lot of the stuff has been developed using was you have like position, momentum there, and okay, depending on how well we define a position, we're not going to know the momentum as well. Something Heisenberg uncertain. But if we can nail the momentum, it's hard for us to know where it is. Well, I'm just like, well, if you've got this, it's like it's a mass times a speed. That speed is the speed of light, and the mass is the Planck mass. The Planck momentum, which is this is was about the momentum of a baseball hitting hit baseball. Let's see, momentum. Blah, blah, blah. All right. Okay. So basically, if you had a soccer ball traveling at 10 meters per second, so there's a little bit more than the momentum of the fastest serve ever recorded in 2012 from tennis. So you have a tennis ball that was going the mass of a tennis ball. Okay, so I was going at that. All right. So okay. A long story short is the relativistic energy of a photon that had that energy momentum would basically be the Planck energy. So as we can see here. So and, and again, it's all I know. Yeah, if I didn't have a tool like Wolfram Alpha and stuff like this, I never would have been able to like see all these things because it's like little error you go through and oh dude, I did this a lot. I like be going through the oh, I found something interesting. This is gonna be a revelation. It was nothing. It was just a user error or something there. But yeah. All right. See where are we at? Going back to this commenting, Planck mass, second, etc. The grid of the universe, everything snaps to almost everything. Interesting perspective. I mean, I grew up with Legos and Lincoln Logs, and I actually really like Connect, so I like snapping things together. I don't know. I mean, maybe it is. Again, I'm trying to take a perspective where, yes, I know I'm a heretic. I know I am a heretic, but at the same time, it's like I look at things out there, and I'm like, all right, does this have more explanatory power with less? And even like for me personally, hey, I traveled to Portugal with Dad to go to a cosmology conference that Shiloh and Anastasia from Demystify Sci. Shout out to those folks. We're putting on, so it's like, all right, went there, presented a poster, had another episode of Paradigm Drift. That was kind of cool. It's the transition there. I'm like, oh my god, that makes me look like it looks like something from a professional poster or something. I'm like, dang, how did you make me look that freaking shiny with a trance there? And I don't know. Uh, again, the miracles of cinema. But the patterning. Well, this is the thing, and this is what I've taken from the Wolfram Physics Project is that I had my skepticism and things, but as I talked with other folks, especially was like Wilhelm, and I think it was maybe Sahil as well, one of the gentlemen over at the summer school. They had a biology thing, and it showed a branching over time. Like it starts off with the same that branches, and I'm like, isn't there something with like the temperature of frogs that more frogs will develop as kind of like one sex than the other, depending on factors and stuff? And I'm like, I don't know if that's even the thing. I'm sure it's more complicated. I'm not a biologist. And then we were walking along, and then one of the gentlemen, he had taken his shoes off. He had asked if there were a lot of rocks in the path. That eventually got rocky again. He had to put his shoes back on. And then I'm like, I don't know how you could walk through that. He's like, oh, people walk on hot coals. I'm like, how the heck do those people walk on hot coals? And then he said something so smart, and I felt like such a noob. He's like, you don't just walk on hot coals. What are you crazy? He's like, no, you build up to it. It's kind of like, yeah, it's like if your feet are being exposed to something, yeah, they're going to develop thicker and stuff. And I'm like, oh, I'm an idiot. I used to go to the gym. You would develop calluses and stuff on your hands. And as those calluses got thicker, you could hold more weight and it wouldn't tear at your hands. I'm like, why would I assume my feet didn't operate any differently? I hadn't considered that because I don't walk around barefoot all the time. Exes would do that, but just wasn't really a thing for me. And then I'm like, wait a second. If you did the inverse of that, so rather than exposing your feet to a bunch of tough terrain, if you were to, I don't know, wash your feet on a frequent, regular basis with a whole bunch of, I don't know, like baby soaps and stuff, maybe your feet would develop very soft and not be able to walk on coals and be extremely sensitive. I'm like, wait a second. If that graph were to start to, hold on, I've got the graph here somewhere. Is it, well, that one? Uh, oh God, what was that even thinking? But no, it literally just. Oh, where is that? I had that somewhere. Literally, what's the guy? No. Wow, I've taken far too many screenshots of far too many different things. Oh God. If anybody's ever read the mixed up files of Mrs. Basil Lee Frankwilder, I feel like I feel like I might be the dude equivalent of that. Like, oh my God, where are all these files and stuff like that? It's like, who knows? It's some screenshot of something from years past or something. Uh, okay, I don't have it here right now. Was that they created? Okay, I have no idea. Uh, so yeah, basically, long story short is I'm like, when you're looking at like the very simple rules, I looked at that and I'm like, okay, now. Also, the interesting thing, this is just something from Stephen Wolfram we can wrap up with, is number one, I think Closer to Truth had a newer interview with him recently. They're releasing in parts. And I think what Stephen had said was that one of the interesting things about simple rules is the universality of computation. Once you have something that's universally a form of universal computation, you could essentially not just have an adding machine, a multiplying machine, blah, blah. You would do basically all computation. And that's interesting. So that's why I'm gaining more and more of an appreciation for the framework. I'm conceptualizing things as rules. I'm just like, it's just not a finite. You're just going to invoke infinity and stuff like that. It's like, it kind of sounds like the rule he had, but it is more of a distinctive way to think about it. And at least as I take it more seriously, I'm like, okay, then maybe there's something there. But ultimately, it's going to depend on what helps you best consider these things. For me, sometimes I look at just like anime and stuff like that. Some folks, perhaps, if you happen to be a computer scientist like Rick, maybe the algorithms are eternal. I mean, that kind of seems, well, we would need an operating system. Oh, okay. So if we had an operating system, this is getting very computational very quickly. I'm sure Stephen Wolfram would love this, but that might intuit that you might need other computers things for it to run. I have no idea where a power source might be, but I actually need to leave it there because I need to. Let me just check to see if Fizz is. I talked earlier, and she was supposed to be around. Let me see. Let me just consult my thingy of. Okay, so for those of you that would like to join from some silliness and debauchery, we will be talking a little bit about science. Uh, Simulation theory. Well, all I know is who knows. Maybe we're in the Matrix. Maybe it's like American Dad. Maybe we're just all in the goo. Who knows? Rick is conjecturing that what we need is another computational architecture. I think that's what a lot of quantum folks are trying to do now. Whether or not that pans out in whatever way, I don't know. But also, basically, what we're going to be talking about is apparently the fake news we did a few weeks ago about Uranus's new moon. We can actually use that title now because apparently James Webb took a long, hard look at Uranus and discovered a new moon. I'm going to hell. So, other than that, for those who would like to join us in a little bit, feel free. Other than that, peace out, everybody. Take care of yourselves, and tomorrow we'll be talking about the Planck temperature. So, it's open for a better tomorrow.